video, we'll tackle the characteristics of capacitors. So let's first examine the relationship between the charge Q and the voltage that is being applied to the capacitor. So let's say we have a capacitor. So the voltage across it is identified as V sub C. And let's say this capacitor is being connected directly to a voltage source V sub S. Now, if we do this, um, the capacitor will actually charge immediately with a Q equals to the relationship that we have covered earlier, which is C times the voltage applied to the capacitor. So since V sub C is equals to V sub S, so we have the Q there stored on the capacitor as C V sub S. Now let's say we charge the capacitor via a resistance. So let's say we have a series RC circuit, and the circuit is connected to a voltage source V sub S. Now when we do this, the capacitor will still charge, but this time on a gradual manner. In fact, it will be charging the capacitor in an exponential manner given by this relationship. Um, we'll derive this later if once we go to um, a more detailed examination of RC series circuits. Now let's call this equation 2. The rate of charging, so the capacitor is still being charged, but in, in an exponential manner, and the rate of charging is actually inversely proportional to the resistance that is in series with the capacitor. So meaning that the larger the resistance, the slower the charging of the capacitor will be. Now the rate of charging decreases as the voltage across the capacitor rises until it ceases when the voltage across the capacitor equals the charging voltage. So we can say that once charging stops, um, we say that the capacitor is actually fully charged. Now let's say we differentiate the equation 1. So equation 1 is this one. So let's differentiate both sides with respect to time. So we get this result. So this is a very important relationship that says that the current that is flowing towards the capacitor is actually proportional to the time rate of change of the voltage across the capacitor. Now if we apply this to the series RC circuit, we have an I that is a decaying function that starts at the maximum value V sub S over R, and then as time progresses, this current will actually decay towards a zero value. Now this equation number 3 tells us several things. First, that the current through the capacitor depends how fast the voltage is changing. So the higher the change of the voltage, the higher the current. Now when V sub Z is increasing, the current is actually directed towards the capacitor. That has a magnitude that is proportional to how fast that V sub C is changing or increasing in this case. When V sub C is decreasing, that is, we have a negative slope, that means the current is actually flowing away from the capacitor. And how fast is the current flowing again depends on the magnitude of dBc dt. Now, this equation 3 also shows us that the the voltage V sub C across the capacitor cannot change abruptly. So let's say it changes from a particular value and then changes immediately to zero. That cannot happen because that would mean that the slope will actually be very high. Ideally, it can be infinite. And that means uh, I must be very high as well, as shown by equation 3, or ideally infinite, which is impossible to happen. Now, for the current voltage relationship, uh, we can also solve for the voltage across given a current function. Um, and if we simplify this, so the voltage is actually equals to the integral of I dt plus an initial value of the capacitor. So initial voltage of the capacitor. Now simplifying this shows us that the voltage across the capacitor is really the voltage due to the change in the accumulated charge plus any initial voltage. For the power and energy, um, the power absorbed or released by the capacitor uh, st still follows the equation for power. So we simply multiply the voltage and the current. But since current is C dV C dt, we can use this and plug this into the equation for power. The energy absorbed or released by the capacitor can be derived by simply integrating the formula for P dt. So since P is given by this one, we can use this and plug it here and you will get 1 half CVC squared. And since we have a relationship Q equals CVC, we can also express the energy absorbed or released by the capacitor in terms of the Q that is being stored by the capacitor. So in our next video, we're going to give some examples on how this behavior can be analyzed.